This resource is the first in a 5-part series on the normal distribution. Part 1 looks at the basics of the normal distribution. We discuss the distribution about the mean and the probability of an amount lying between integral multiples of the standard deviation. Part 2 considers the process of normalizing a value. Part 3 considers the probability a normally distributed value will lie in some range. Part 4 combines the ideas presented in Parts 2 and 3, finding percentages for examples that require normalizing the value first. Part 5 looks at how to find the variable value that define various percentile ranks in a population, which means a specified percentage of the population is less than that value for the variable. Think about some situation with a range of values. Maybe it is the heights of adult females, or maybe the weight of a newborn kitten, or even the length of a song on the radio. How are these values spread out? Most of the values are centered about the mean. Outliers, values that are significantly different from the mean, do exist, but do not appear often. This is the idea of a normal distribution. Most members of a population exist close to the mean. In fact, if the population is normal, we know exactly how likely it is that an individual is within some number of standard deviations of the mean. If we look at the frequency of values for a normal distribution, we get a well-defined graph. The bell curve has a center point of the mean and is actually the graph of the function shown for a given mean mu and standard deviation sigma. Fortunately, we will not have to find these function values. They are very well defined. However, we will need to familiarize ourselves with the curve and its features. The first thing to note is that the graph is symmetric about the mean, so we are equally likely to have a really high score as to have a really low score. The graph is labeled according to the number of standard deviations above or below the mean. The probability of having a score somewhere between one standard deviation below the mean through one standard deviation above the mean is 68%. 95% of all scores are between 2 standard deviations above and below the mean, and we are 99.7% likely to have scores within 3 standard deviations of the mean. How exactly does this relate to the real world? Let's see some examples. Analysis of the 1999 census shows that the average height of women aged 20 through 29 was 64.1 inches with a standard deviation of 2.75 inches. Assuming that the height of women in that age range is normally distributed, between what two heights would we expect 95.4% of women to have? The key to solving this quandary is to think about the breakdown of the normal curve. We recall that we saw that percentage under the graph. In fact, it turns out that 95% of the area under the normal curve lies between the x values that are 2 standard deviations above or below the mean. First, let's find the lower limit, which is the mean minus 2 multiplied by the standard deviation. We have a mean of 64.1 and a standard deviation of 2.75. When we plug those values in, we get a lower limit of 58.6 inches. Now we will find the upper limit as the mean plus 2 times the standard deviation. Plugging in our values, the upper limit is 69.6 inches. So 95.4% of women with ages between 20 and 29 have a height that is somewhere between 58.6 and 69.6 inches. But what if we want to find the percent of the population that lies between specific values? Suppose the average weight of a 10-week-old kitten is 25 ounces, with a standard deviation of 4 ounces. If the weight of kittens is normally distributed, what percent of kittens in that age range are between 21 and 33 ounces? The key to this problem is that the weight is a normal distribution. If we look closely at the lower limit, we recognize that the weight is exactly 4 ounces, or 1 standard deviation below the mean. The upper limit is 8 ounces, or exactly 2 standard deviations above the mean. But how does this help us? If we look at our graph of the normal curve, we realize that 68.2% of the population is between 1 standard deviation below through 1 standard deviation above the mean. Also, 13.6% of the population is between 1 and 2 standard deviations above the mean. If we add those two percentages together, we realize that 81.8% of 10-week-old kittens weigh between 21 and 33 ounces.